Reviewing enterprise routing protocols. This segment describes considerations for selecting the most appropriate network routing protocol. So first, routing protocol features are discussed, followed by a description of various routing protocols appropriate for the enterprise use. The video discusses why certain protocols are suitable for specific modules in the enterprise architecture. It concludes with a description of some advanced routing protocol deployment features, including redistribution, filtering, and summarization. Routing protocol features. So you've got the distance vector versus the link state. Okay? So there are many ways to characterize routing protocols, including static versus dynamic routing, interior versus exterior routing protocols. You've got distance vector versus link state versus hybrid protocols. Okay, so you also have routing protocol metrics, routing protocol convergence, flat versus hierarchical routing protocols. So basically, on this slide, we will be talking about distance vector and link state comparison. Okay, so there are protocols that are classified to be distance vector, which includes RIP and EIGRP. Okay, so these are distance vector. EIGRP is considered to be the hybrid protocol. Okay, now link state, such as OSPF and ISIS, these are types of the link state routing protocols. Okay, now distance vector protocol characteristics. Well, slow convergence, easy implementation and maintenance, and limited scalability. Okay, whereas for the link state protocol, it is fast convergence, good scalability, less routing traffic overhead, and more knowledge needed for implementation and maintenance. Again, several protocols are running under distance vector, which includes RIP and EIGRP. And for the link state, well, a popular OSPF is being considered. Now let's focus on the distance vector protocol. In distance vector protocol, routing decisions are made on a hop by hop basis. Okay, each router relies on its neighbor routers to make the correct routing decision. So the router passes only the results of this decision, which is its routing table, to its neighbors. Distance vector protocols are typically slower to converge and do not scale well. However, they are easy to implement and maintain. So again, examples of distance vector protocols includes RIP, okay, both RIP version 1 and RIP version 2, and the Enhanced Interior Gateway Routing Protocol, or the EIGRP. Now for link state protocol, each router floods information about itself, its link states, either to all other routers in the network, okay, or to part of the network. We call it area. Now each router makes its routing decision based on all the received information and using the shortest path first, or SPF algorithm, also known as the Dijkstra's algo, which calculates the shortest path to any destination. The link state protocols are fast to converge, have less routing traffic overhead, and scale well. However, because of their complexity, the link state protocols are more difficult to implement and maintain. The IP link state protocols are OSPF and the integrated ISIS. So the third type of protocol that I have mentioned earlier is what you call hybrid interior gateway protocol, which is the Cisco's EIGRP. Now, I have mentioned earlier that this is part of the distance vector. Okay? Now, it is an advanced distance vector, making it a hybrid. Okay? So, EIGRP has characteristics of both distance vector and link state protocols. It combines distance vector behavior with some link state characteristics and some proprietary features. So EIGRP routing protocols are running only on Cisco devices. So if you are using non-Cisco devices, so it is recommended to use OSPF. So EIGRP is a fast converging and scalable routing protocol. Now let's look at the interior versus exterior routing protocols. So interior, okay, or IGPs, routing inside the autonomous system. Again, autonomous system pertains to a network being maintained by a single administrator. So fast convergence and easy configuration, low administrator influence on routing decisions. Now for the exterior gateway protocols or EGPs, routing between autonomous systems, slow convergence, and more complex configuration, and high administrator influence on routing decisions. So if you want to learn more about interior and exterior routing protocols, so go ahead and check the supplementary videos. Okay, now where do we apply interior and exterior routing protocols? So as what I've mentioned earlier, okay, interior or IGPs are the routing protocols implemented within the autonomous system. So if this is an enterprise A, within this network, we are using interior gateway protocol. Example, EIGRP. Okay, assuming that this is autonomous system 2, if you have autonomous system 3, again, this is maintained by a different single administrator. And within this network, autonomous system 3, we are running IGP, specifically OSPF. Now on ISPC or AS1, okay, so within the system, they are using IGP ISIS. But connecting these different autonomous systems, that is where we use the exterior gateway routing protocol or EGP, like the border gateway protocol or BGP. Okay, so interior versus exterior routing protocols. So flat routing protocols propagate all routing information throughout the network. So these are to be classful routing protocols. Okay, so these are the old routing protocols which follows the subnet mask. Okay, this is not appropriate for large networks. So example of routing protocols which are classful and flat are RIP version 1, okay, the old IGRP, which now we are using EIGRP, and RIP version 2, which is classless. Okay. Now for hierarchical routing protocols, divide large networks into smaller areas or subnets. So these are said to be classless routing protocols. And usually we are using EIGRP. Okay, again, EIGRP is a proprietary protocol from Cisco. If you are using non-Cisco devices, so better use OSPF, okay, or ISIS. Okay, so also for the hierarchical routing protocols, so limited route propagation between areas. All right, so flat versus hierarchical routing protocols. So again, we mentioned about flat routing protocol earlier. So flat routing protocols have no means of limiting route propagation in major network. That's within Class A, Class B, or C network environment. These protocols are typically classful distance vector protocol. So the key point, flat routing protocols propagate all routing information throughout the network, whereas hierarchical routing protocols divide large networks into smaller areas. Okay, so two examples of flat routing protocols are, again, RIP version 1 and RIP version 2. Take note, however, that RIP version 2 is already a classless protocol. Now, this figure here illustrates a flat network and hierarchical network. Now, for the hierarchical routing protocols, to solve the problems associated with flat routing protocols, Additional features are implemented in hierarchical routing protocols to support large networks. For example, some support an area-based design. So hierarchical routing protocols are typically classless link state protocols. So classless means that routing updates include subnet masks in their routing updates. Therefore, the routing protocol supports VLSM, or the variable length subnet mask. Routing protocol convergence. So different routing protocols need different amounts of time to converge in a given network. So although the convergence depends on network's topology and structure, pure distance vector protocols are slower to converge than link state protocols. The use of periodic updates and the hold down mechanism are the main reasons for slow convergence. As a result, the fast converging protocols should be used when the network's convergence time is crucial. Now, as shown here in the figure, different routing protocols need different amounts of time to converge in a given network. So link state protocols usually converge much more quickly because they instantly propagate routing updates. Okay? So whenever the change occurs in a link state, okay, that's OSPF, a link state update is flooded throughout the network or within the entire network. So there is no need to wait for the hold down timer to expire or for the next periodic update as with distance vector protocols. Now let's talk about this hybrid EIGRP, or the Enhanced Interior Gateway Routing Protocol from Cisco. So EIGRP is a special case because it incorporates the distance vector principle of metric propagation. It means it sends only the best routes to the neighbors. However, it does not have periodic updates, nor does it implement the principle of hold downs. So the most distinct feature of EIGRP is that it stores all feasible backup routes in its topology table. So when a backup route exists for a lost destination, the switch over to the best backup route is almost immediate and involves no action from other routers. Therefore, very fast convergence can be achieved with proper EIGRP deployment. Okay? EIGRP characteristics. So as I mentioned earlier, EIGRP is proprietary. Okay, it's a Cisco proprietary protocol for routing IPv4. EIGRP can also be configured for routing IP version 6, okay, Inter-Network Packet Exchange IPX, and AppleTalk traffic. Now, EIGRP is an enhanced version of the old IGRP, which is pure distance vector protocol. So EIGRP, however, is a hybrid routing protocol. It is a distance vector protocol with additional link state protocol features. So EIGRP features includes the following. So it uses a triggered updates. EIGRP, take note, has no periodic updates. Uses a topology table to keep all routes received from its neighbors, not only the best routes. Establishes adjacencies with neighboring routers using the hello protocols, just like in OSPF. Okay, uses multicast rather than broadcast for communication. It supports also VLSM. Supports manual route summarization. EIGRP summarizes on major network boundaries by default. Okay, but these features can be turned off and summarization can be configured at any point in the network. So it can be used to create hierarchically structured large networks and supports unequal load balancing. Okay, so EIGRP uses the diffusing update algorithm to determine the best path OSPF uses Dijkstra's algorithm. Now let's talk about the open shortest path first routing protocol, or the OSPF. OSPF is a standardized protocol for routing IPv4. Okay, so it was developed in the year 1988 by the Internet Engineering Task Force, or ETF, to replace RIP in larger, more diverse media networks. Okay, so in 1998, minor changes in OSPF version 2 addressed some of the OSPF version 1's problem while maintaining backward compatibility. So OSPF was developed for use in large scalable networks in which RIP's inherent limitations fail to satisfy requirements. So OSPF is a superior to RIP in all aspects, including the following. Okay, so you've got, it converges much faster. It supports VLSM, manual summarization, and hierarchical structures. It has improved metric calculation for best path, okay, and it does not have a hop count limitations on RIP version 1 and 2. So at its inception, OSPF supported the largest networks. OSPF Hierarchical Design. So although OSPF was developed for large networks, each implementation requires proper design and planning. This is especially important for networks with 50 or more routers. Okay, so the concept of multiple separate areas inside one domain, or AES, was implemented in OSPF to reduce the amount of routing traffic and make networks more scalable. So in OSPF, there must always be one backbone area, which is area 0, to which all other non-backbone areas must be directly connected. So you've got area 1 here, area 2. This non-backbone area should be directly connected to area 0 or backbone via the area border router, or ABR. Okay? Now, a router is a member of an OSPF area when at least one of each interfaces operates in that area. So, router that resides on boundaries between the backbone and the non-backbone area are called area border routers, or ABRs, and have at least one of each interface connected to each area. So, the boundary between the areas is within the ABR itself. So if external routes are propagated into OSPF AES, the router thus redistributes the routes, and it is called Autonomous System Border Routers, or ASBRs. Okay? So careful design and correct mapping of areas to the network topology are important, because manual summarization of routes can only be performed on ABRs or ASBRs. Again, when you say ASBRs, these are routers connected to non-OSPF networks, example, the ISPs. So traffic sent from one non-backbone area to another always crosses the backbone. For example, the Area 1 ABR must forward traffic from Area 1 destined for Area 2 into the backbone. The Area 2 ABR receives the traffic from the backbone and forwards it to the appropriate destination inside Area 2. OSPF characteristics. OSPF is a link state protocol that has the following characteristics for deployment in the enterprise networks. So first, fast convergence. Okay, so OSPF achieves fast convergence times using triggered link state updates that include one or more link state advertisements, or LSAs. So LSAs describe the state of the link on specific routers and are propagated unchanged within an area. So therefore, all routers in the same area have identical topology tables, each router has a complete view of all the links and devices in the area. So depending on their type, LSAs are usually changed by ABRs when they cross into another area. So the next one is, it's a very good scalability. Okay, OSPF multiple area structure provides good scalability. However, OSPF's strict area implementation rules require proper design to support other scalability features such as manual summarization, okay, on ABRs and ASBRs, stub areas, totally stubby areas, and not so stubby areas, or NSSA. Okay. Next is reduced bandwidth usage. Along with the area structure, the use of triggered, not periodic, okay, so we're talking about the triggered updates, and manual summarization reduces the bandwidth used by OSPF by limiting the volume of link state propagation. Okay, and the last one would be, of course, the VLSM support. So because OSPF is a classless routing protocol, it supports VLSM to achieve better use of IP address space. So to know more about OSPF, you can go ahead and check the supplementary video. Okay, so that discusses the details about this routing protocol. Next would be the ISIS. So ISIS was developed by Digital Equipment Corporation, or DEC, as a dynamic link state routing protocol for the Open Systems Interconnection OSI protocol suite. Okay, so the OSI suite uses connectionless network systems or service, so we call it CLNS, to provide connectionless delivery of data. And the actual layer 3 protocol is Connectionless Network Protocol, or CLNP. Now, CLNP is the OSI suite solution for connectionless delivery of data, similar to IP and TCP/IP suite. So ISIS uses CLNS address to identify the routers and build the link state databases, or LSDB. Next would be the Border Gateway Protocol. This is an example of EGP. Okay, so BGP is an EGP that is primarily used to interconnect autonomous systems. BGP is a successor to EGP. The Exterior Gateway Protocol. Okay, so note the dual use of EGP acronym here. Okay, so because EGP is obsolete, BGP is currently the only EGP in use. All right, so the key point here for BGP is that the main goal of BGP is to provide an inter-domain routing system that guarantees a loop-free exchange of routing information between autonomous systems. So BGP routers exchange information about path to destination networks. BGP Network Implementation. So in this figure here, okay, BGP is used to interconnect multiple autonomous systems. Because of the multiple connection between autonomous systems and the need for path manipulation, the use of static routing is excluded. So AS65000 is multi-homed to 3 ISPs. Okay, AS65500, okay, AS65250, and AS64500. Internal BGP. So when BGP is running between routers within one AS, it is called internal BGP, or IBGP. IBGP is run within an AS to exchange BGP information so that all internal BGP speakers have the same BGP routing information about outside autonomous systems. And so that information can be passed to other autonomous systems. As long as they can reach each other, routers that run IBGP do not have to be directly connected to each other. Static routes, or routes learned from an IGP running within the AS, provides reachability. When BGP runs between routers in different autonomous systems, it is called external BGP or eBGP. Routers that run eBGP are usually connected directly to each other. Recommended enterprise routing protocol comparison. Okay, so basically, this would yield to two of the most popular interior gateway routing protocol, EIGRP and OSPF. So they are both fast convergence. They are very good scalability. Okay, these two both uses VLSM. Okay, multiple network layer protocol support. Well, EIGRP, yes. Okay, OSPF, no. Mixed vendor devices. For OSPF, yes, you can use OSPF routing protocol on any brand of routers. Unlike EIGRP, which is supported only on Cisco equipments. This is proprietary here. Now, to summarize, reviewing the enterprise routing protocols. So protocols with hierarchical and linked state attributes supports the fastest network convergence. EIGRP and OSPF are the recommended IGPs for the enterprise. EIGRP is a Cisco proprietary for routing IPv4, IPv6, IPX, and AppleTalk traffic. OSPF is a standardized protocol for routing IPv4, developed to replace RIP in a larger scale, more diverse media networks. It can also support IPv6. BGP is a representative EGP. It is primarily used to interconnect autonomous systems or to connect enterprises to an ISP.